we discussed 3 ways of solving constraints: analytical, procedural, and numerical. This video will focus on the numerical approaches to solving constraints. For problems that cannot be solved analytically or procedurally, a numerical approach can be used. Numerical approaches consist of an iterative process that searches for a solution. They often use heuristic rules to guide the search. Many different types of iterative solvers exist. 2 types are global solvers and local solvers. Global solvers generate and test many alternative solutions. Local solvers improve one solution over many iterations. In this video, we will look at an example of a global solver. For global solvers, we will look at a generate and test solver. In the videos that follow, we will look at 2 types of local solvers: a particle solver and a spring solver. The generate and test approach is a simple brute force search strategy. It is often very effective. It generates many alternative solutions and tests to see which one is the best one. It requires a systematic way to generate and test solutions. For this example, the problem will be to find the largest inscribed rectangle inside a polygon. Although the problem might seem simple, it turns out to actually be very complex. As a result, we will use an iterative solver. For this example, we will focus on a slightly simpler version of the problem: finding the biggest inscribed polygon inside a convex polygon. In addition, we will only look for polygons that are aligned with one of the edges. The first task is to find a systematic way of generating solutions. The solutions that are generated should all be guaranteed to be valid. In this case, we will focus on an algorithm for finding the biggest rectangle along one edge. If that can be solved, then it can be repeated for all edges. The algorithm starts by generating a sequence of points along the edge. The point spacing is specified using a parameter. Smaller values will result in greater accuracy, but at the cost of more computation. For each point, 2 rays are generated. First array is generated perpendicular to the edge. At the point of intersection with the polygon boundary, another ray is generated parallel to the edge. This then generates another intersection. This results in a total of 3 rectangle vertices. The 3 vertices are used to generate a rectangle. In some cases, the third point may need one additional step to adjust its position. We will see that in the next example. The process repeats on all edges. Here is another edge. Again, a sequence of points is generated. Again, the 3 points are generated. In this case, it can be seen that there is a problem. The third intersection point is beyond the extent of the edge. In such cases, an additional step is required to pull the intersection point back. A valid rectangle is now generated. Repeating this process for all points on all edges results in a large number of rectangles. Note that in the solver, these rectangles are not generated as geometric entities. Instead, they are calculated mathematically, using vector algebra. This will significantly improve performance. For each edge, the biggest rectangle is chosen. And then for the rectangle as a whole, the biggest edge rectangle is chosen. This algorithm could be adapted to also handle concave polygons. Note that there are cases where the largest polygon is not aligned with an edge. Whether the algorithm's assumptions and approximations are acceptable depends on the use case. In the next video, we will look at an example of a particle solver.